Today we're going to solve 2958, length of the longest subarray with at most k frequency. This is a classic sliding window style problem. And within this solution, I'm going to show you both kind of the intuition that leads you to understanding that this problem is a sliding window and my own personal approach to designing, right, to developing a sliding window solution, a generalized approach that I found to be very effective, right? Because even when you understand that something's a sliding window, it can be kind of difficult to actually develop a solution while considering the edge cases, right? Because when you have a sliding window, what you basically have is like a left pointer and a right pointer, and you're shifting, you're moving things, and you're like, okay, well, what do I do if they touch each other? What do I do if, like, what can my left pointer exceed my right pointer? How do I decide what lengths are, etc.? Okay, so that's it. Let's go ahead and get right into this. So you're given an integer array nums and an integer k. The frequency of an element x is the number of times it occurs in an array. Hopefully that makes sense to you. The idea is only that you have an array, like, for example, you should probably already understand what a frequency is, right? With, I don't know, 4, 3, 4, 7, 2, 3, 4, right? What's the frequency of 4? Well, the frequency of 4 is 2. Why is the frequency of 4 2? Well, because 4 occurs 3 times, right? Because there's this 4, there's this 4, and there's this 4. What's the frequency of 3? Frequency of 3 is 2 because there are 2 3s. What's the frequency of 2? The frequency of 2 is 1 because there's 1 2. What's the frequency of 7? The frequency of 7 is 1. Right. All right. An array is called good if the frequency of each element in this array is less than or equal to k. Return the length of the longest good subarray of nums. A subarray is a continuous, non-empty sequence of elements within an array. All right, so we're trying to find a subarray. We want to maximize the length of a subarray that meets the conditions where the frequency of any one number is less than k. Okay, so let's go ahead and look at an example. And I'm going to delete this because it's not really that useful. It's just to establish this idea of frequency if that was something you were confused by. But of course, if you're doing a medium problem, this should be a concept, frequency, arrays, what are integers, what are lists. These are basic concepts you should already understand, but it's neither here or there. Example, nums equals 1 2 3 1 2 3 1 2 1 2 3 1 2 3 1 2. All right. Now it says the answer here is 6. So meaning that we can find a subarray of length 6 that meets these conditions. And it's saying the longest possible subarray is here. 1 2 3 1 2 3. Right here. Right? Because when we look at this array, what's the frequency of everything that's within the array, right? Well, the frequency of 1 is 2. So we're good, right? Because our k value is 2. So all of our frequencies need to be less than k. That's good. What's our frequency of 2? Our frequency of 2 is 2, which is less than k, less than or equal to k, right? And our frequency of 3 is 2, which is less than or equal to k. So we're good. And why can't I add an additional element? Well, if I was to add this additional element, that would increase my frequency of 1 to 3, which is not less than k, which causes it to fail. All right, and then it can be shown that, in any orientation, this is indeed the longest array that you can create. A subarray that you can create while meeting these conditions of the frequency. Okay. K equals 1 here, right? You can only have 1 of each element, right? So 1, 2, can't add another 1 because there's a 1 there. 1, 2, 2, 1, again, it can be shown. This 5, K equals 4. I mean, it's obviously going to be 4 because all you have is 5, so the longest you can have is only 5s, and you can only have as much 4 of them. So what's the intuition of this problem to make this work? Well, I guess what led me to thinking about whether or not this was a sliding window is like, I'm trying to maximize the size until I can't. And if I can't anymore, I have to remove things because I won't be able to in the future either. Okay? And what I mean by that is like, let's look at an example, a better example that might lead you to some sort of intuitive understanding about why this is a sliding window problem. Okay, so let's say that nums was, let's see. Let's say k was 1. Okay, very simple. K is 1, right? And then we say our array was 1, 2, 3, 4, 5, 1, 2, 3. All right. Actually, let's do this a little bit different. Let's say this was 0, 1, 2, 3, 4, 5, 1, 0, or again, always finding good examples is crucial when you're solving a Leetcode problem, right? You need to be able to determine examples that are going to reveal something about the problem, right? I can never make that point enough. That is what always leads you to the solution. So try to think about examples with weird edge cases that are simple enough to solve quickly that will reveal something about the answer. Okay. Now, if I was just to like say, okay, how am I going to build this thing? Well, let's start building it out from here, right? I'd add a 0, I'd add a 1, I'd add a 2, I'd add a 3, I'd add a 4, I'd add a 5. And when I add this 1, it becomes problematic, right? When I add this second 1, it's an issue because my k value is 1, meaning that I have to have less than 1 of each value, right? So when I add this 1, I'm saying, it's not going to work. This is not going to work. It's not going to work because now I have 2 1s. So I need to get rid of a 1, right? So I can either... I need to get rid of a 1, right? And I guess you can think about directionality. I'm not going to go down that rabbit hole here now. But, you know, if I have this 1 here in the way, right? This 1 is what's causing an issue with me being unable to continue to scale out this system. All right? So what I'll do is I'll just say, well, this isn't working anymore. So I need to start removing elements in order to make this work. Right, so even though I added 1, I added 2, I added 3, I added 4, I added 5, I added 1. When I got to this length, I said, you know what, this actually isn't going to work anymore. Right, and then I still look at this and I say, okay, does it work now? No, it still doesn't work because I still have too many 1s. So I'll remove this and move this over. And now I found another subarray that works, right? And then I can continue on, okay? So I hope what I'm doing here makes a little bit of sense. What I'm basically saying, and I'm going to go through this again a little bit more thoroughly, is that, you know, these 1s, since k is 1, they can't be together, right? Because I can't have more than 1 1. So as soon as I'm trying to maximize the length of this array. As soon as I get to a spot where I have more than the ones that I want, I need to start removing things to get rid of it, right? If I had, you know, a bunch of elements, let's just say different elements over here, right? Like y, and a bunch of values here where it all worked out, right? And a bunch of values here, y, where it all worked out, right? So let's say that these dots represent just random values, but they're all unique. They're all different. And the only 2 values that are the same are this y and my k equals 1 again, okay? What happens here is, you know, I can grow this thing out all the way to here, right? But as soon as I touch these y's together, it separates out, right? I can't have these things together. So if I add this y, I can't put this one in the system, right? So I have to start removing elements until I get rid of everything except for this y, and then I can keep building out, right? So what I'm basically doing is greedily, right? A lot of sliding windows problems are just like greedy solutions where, you know, I'm trying to build out, and the second I get to a case where I can't add it, right, I don't meet the situation, I need to start removing things until the situation works again, okay? So what's going on here, and I'll do this again. This one problem is if I keep track of the frequency of everything, right? So if I have a frequency table to the side and I say, okay, I'll look at this element. I'll start with my left pointer here. Say, okay, my frequency of 0 is 1. And then I move my left pointer over and I say, okay, my frequency of 1 is 1. Okay, then I move my left pointer over and I say, okay, my frequency of 2 is 1. Everything's good so far because it's less than k, right? I added a 2. Is my frequency less than k? My k value is 1. Yes, we're good, right? I add a 3. Say, okay, my frequency value is 1. Is that less than equal to k? Yes, we're good. I add a 4, add a 5. I'll just fast forward to that point. So I add a 4, I have 1. I add a 5, I have 1. And then when I try to add a 6, what happens? So now when I add a 6, when I add a 1, what happens? I add a 1, and this updates to 2, and I say, now I'm in a situation, God damn it. This left pointer needs to be over here, right? This is a right pointer. So I add a 1, add a 2, add a 3, add a 4, add a 5, add a 1. I get to this case, I say, okay, I maximize my length, and I'm having an issue where a K value, right, one of the frequencies for a value is greater than 1. So I need to start removing things to make this work, right? I've extended myself too far, and I could extend myself. I can move this back, but that'll just put me back in situations I've already encountered. So what I should do instead is start removing things until this situation is fixed, right? So I'm like, okay, I'll remove this 0. Okay, I'll remove a 1. And as soon as I remove that 1, now I have 1, 1 again, and I can continue on with this game. Adding a 6, adding a 7. Adding a 6, adding a 7. Okay, so basically what we're doing here, right, and this is such terribly written example here today, I don't know what's going on with me, is the sliding window is, okay, I'm trying to maximize what I can get, and since it's a subarray, as soon as I find something that breaks the situation, I can just start removing things to fix the situation, right? So I'm basically trying to maximize what I can get, and as soon as I get in a situation where it's like, okay, this is no longer valid, what can I do to make this valid? The only thing I can do is remove things from the front because I'm adding to the back. All right. So maybe this explanation is not that great, and that's okay. But maybe you'll appreciate my code here in terms of how to manage creating a sliding window problem. Okay, so what we're going to do is we're going to have our answer res, and res represents what we're going to return in the end as like our solution, right? The length of the longest good subarray. All right, and then we'll keep track of everything that we find, right? So I'll do that as a frequency array, a frequency default dict of the default value 0. Okay, and the way that you can do kind of, we'll say left equals 0 in the beginning. Now the way you can do sliding windows kind of nicely is you say, okay, I always keep track of my left value, and then I just increase right as I go through. Okay, so for R in range length of nums, you say as well, I'm going to add R to my set. So I'll say if f of R, f of nums of R plus equal 1. Now, if I add it and it creates an issue, I need to start moving the leftover. So I'd say while the frequency of the nums that I've added, because only the num I'm adding can create an issue, right? So I just thought of a better way of describing this. It's weird how that always happens, you know. I think. God forbid I lose my thought here. My train of thought, I guess. Right? But one other way, if you can think of this, right, is you could say, well, let's imagine that the system here is all good. We'll color coordinate this here. All right, so whatever these values are. Okay? And then let's say we wanted to add a new value. So what I'm basically doing is I'm saying, all right, if I add a new value C, is that still good? Because everything before me is good. So if I add a C and it's still good, then this whole thing is good. But if I add a new value C and it exceeds the value K, this new value C, because if this whole thing is good, then all the values within it are good. So I don't need to focus on all the values. I just need to focus on what happens when I add a C. If I add a C and it's still good, then everything's good and I just keep on going on my way. And maybe I look at D next. But if I add a C and it's not good, well, then I need to find the spot where that C is that's causing an issue and cut everything else off except for that value. Right? So if I add a C, there's either two things. This is all good. I add a C and we're good. So that would correspond to being a new system of everything being all good. Or I add a C and it's not good. That means that now I have some other situation where the C value is not happy. That meaning that this new system gets reorganized here, right? So I'm assuming everything's good within my sliding window. As soon as I add something, I say, okay, is this good? If it's good, then they can be combined. If it's not good, then I need to move my value over until it becomes good again. Good, okay? So while, and there's probably a formal kind of inductive proof, right? Because there's kind of this inductive idea of like, if it's good, it's not good, and you always find the maximum. I'm not going to go through it. I hope that intuitively makes sense, right? So what you can say is, I'm going to add it and then check if it's good. Well, if it's not good, then the new value I have is greater than k. So I'm going to have to keep removing elements from the left until the new value I add doesn't exceed. So I basically have to find the last instance of this value. Well, I have to find the oldest instance of this value. So I just thought of maybe a faster way of doing this because... No. Because you could fast forward. Nah, I'm not going to do that. Let's just say L plus equal 1. And then you basically have to, so you remove the element that's at the very left from your array, and then you add one to L. So now it's a little bit smaller. So while it doesn't work, this will keep going. So you can know at this point, everything within your system is good. So you can say res equals the max of whatever you think res is. And then what's the length of the array you're creating, right? What's the length of this corresponding array that you create? Well, you have your right value and your left value. So the difference between that plus 1 would be the length. Okay, so that's R minus L plus 1. But I'm wondering about this L thing, because I guess you could technically not keep track of the frequency. Well, you'd have to know the frequency to know what will be the length. Gosh, guys, I'm sorry. It's just, this works. All right, I'm going to submit this, and then after, you can abandon this solution, because I'm thinking about a different way of doing this, which is faster, but it's only 98%. All right, because technically you could do F, and you could say while... You say if f of nums, so you could do append R. You have to remove the most recent one. So you'd have to pop the first one. So this would have to be a deck then. I don't even know the deck library. So basically what I'm saying here is like, you don't actually need a while loop because you just need to, like, if you added 4, if you added 4 and the most previous, like, and you can only have 3, well then just remove the earliest one. So you just shift your pointer over. You don't need to like slide over, just shift over to wherever that first one is. But I don't even know if this is the deck library. Lambda deck. Someone's screaming at me right now, like that's not the deck library. I mean, I have no idea. Okay, so you'd append R. You would just set L to deck.popleft. Is there such a thing? I don't even know if that doesn't really affect the runtime. It just, makes it way more complicated for no point. But could it still be OVN? This is me just thinking on the spot here, guys. If length of this, right? Because now it's not the number of elements. The number of elements would correspond to the number of things within it. Did I mean pop left? I did mean pop left. Why is it not capitalized? Who made that decision? Camel case. Why needs an argument? Unbound method. Let's just see deck in Python. See, guys, now you're seeing how a real programmer does it. Understanding ideas and finding solutions. It'd have to be this actually plus 1. Right, because that'll be the most recent one, so you need to go 1 past that to make this work. Watch it be slower too. That's usually how it works for me. All right. Why doesn't that work? Whatever, guys. I had a solution that worked already. I'm not going to hold you guys here. So what was the runtime of the solution that worked already? Oh, I really want this to work, though. This is saying 4. This would be 3. You add a 4th one. 3. Oh, I see. Yeah, because when you add these... This doesn't work. Didn't think about that. This does not work because I remove this 2, right? But then it still has this 1 when I add this 1, so it thinks, oh, I'll just remove this 1. But this 2 is ahead of this 1. So I would have to like say, okay, what is my left? And while my left is less than the thing that I'm popping, increase. But that's just the same exact thing as doing a while loop, which is simpler. So no such thing as a free lunch. Think of things on the spot. Sometimes it doesn't lead you to the right answer. But understanding that when you look at an example, like, okay, that doesn't work. But... all right. So with that said, let's look at the run and space complexities. And that didn't even actually add better time or space. Okay. So let's say n is the length of nums. All right. We'll go really fast here, guys. I apologize about that. Time, big O. Well, we go in the range, and you might be tempted to say that this is n squared, right? Because you look at all the elements in nums, and then you have this while loop inside. So you have embedded loops, right? But this loop is corresponding to your L value, right? Because your L value keeps increasing, but your L value will never surpass R, right? So even though there's 2 loops, the L value is constricted by your R value. So when you increase R, you can increase L, but you can never surpass R, right? So as R keeps going through and increases, in the worst case, L will go through the whole array with R, right? So if R goes all the way to the end, then L goes all the way to the end. But if R goes to the middle, L meets at the middle, right? It'll never surpass, right? This L is only going to move through the array once, right? R is only going to move through the array once, and L is only going to move through the array once. But the way that since they're embedded, it kind of like they swap, trades with each other, meaning that, R goes through a little bit, and then maybe L goes through a little bit, and R goes through a little bit more, and L goes through a little bit more. But the idea here is this whole thing and the whole runtime will only at most go through the entire array once. And this for loop obviously only goes through the array once. So even though there's 2 embedded things, this whole thing through the whole process will only go through once, and this will go once. So that's once plus once, big O of n. Right? It goes through n times, and this whole thing through the entire operation will go in n times, meaning that after every loop is exceeded. So that's just O of n, and then we return that value, so that's big O of n. Okay. And then for space complexity, we create F, and then in the worst case scenario, right, every element is unique. So we have to create a little key in our dict for every single element, right? So every element gets a little piece. So in the worst case, that's O of n space. All right, guys, hope you have a beautiful rest of your day. Peace out.